So, good afternoon, students. This is Dr. E. Srinivasa, Assistant Professor of Physics. Today we will discuss about the uh, second year semester 4 optics course. Here you need to know about that the same pattern which you have been already attempted in first year, that is first sem, second sem, as well as the in previous semester, third semester also. Let us discuss about the how many blocks are there. ఇక్కడ ఎన్ని blocks ఉన్నాయనేటువంటి we can observe that four blocks are there. One is the first block is interference, and second block is diffraction, and third block is polarization, and finally last block is lasers and holography. Okay. So in this interference, you need to know about that what is Huygens principles and Young's experiment of light. But before going to discuss all these things, let you know about that what do you mean by optics. Optics means which is entirely related with the light and lenses or glasses. Okay. Where you are using the lenses, and you have to study about the phenomena of the light properties. Okay. So here optics, which is a dealing, which is also a branch of physics and which is going to be dealing with the light. There only we are using the lenses here, whether it is a interference pattern or diffraction pattern. Okay. So everything we are going to be discussing. So in this, how many are there means here? Four blocks are there. First block is the interference, second diffraction, third polarization, and finally lasers and follow. Okay. Let us discuss about the interference. What it tells interference here. Okay. So the thing is that you need to know about the Huygens principle as well as the Young's experiment. Okay. And also you need to find out, and you need to know about the what are the applications of the interference here. And also know about the reflection as well as the coherence. Okay. So here Huygens principle. Let you know that this is the unit 1, Huygens principle. So here there are introduction in this Huygens principle, laws of reflection, and laws of refraction, total internal reflections. Okay. These three comes under this picture to discuss about the Huygens principle. Next is the phenomena of the interference. Interference phenomena which you have been observed in the case of Young's double slit experiment. And here you need to know about the application oriented for the interference here. That is interference, where do you observe, where the interference pattern is going to be caused. So one best example which is in thin films, Palichatti Poralalo. Okay. So here, what do you mean by reflection and what do you mean by refraction? Means here, whenever two different medias are there, whether it is air to denser or denser to rarer. Okay. So if the light which is to be entering and incidenting at the normal on the smooth surface. Okay. So here let us consider that denser media is a glass, rarer media is a air here. So the light ray which is to be incidenting at a normal means there is a smooth surface. The glass means smooth surface. So the thing is that here at the normal incidenting with an incident angle I, so that in the opposite direction, in other direction, and which may the incident ray which may makes an angle theta, that is with the normal, and uh, which may goes in the same media in different direction, that is related to the reflection. But whereas in the case of refraction means here At the normal incidenting, the ray is incidenting and which is going to be making an angle theta with the normal, uh, and which may bends at the normal enter into the one media to the another medium. Rarer to denser or denser to rarer. So that is nothing but a here refraction. So these are the basic definitions. Okay. So here the light energy which is going to be propagating from one place to another place uh, by moving the matter. Matter means which may have a mass, and by the wave disturbance. Wave disturbance means here something is going to be hitting. That means if a pond is at rest, that means a pond means which is full of the water. Water means H2O molecules are there. So those are in a rest. Those are in equilibrium. So whenever you are hitting the surface of the water with a stone here, you are transferring such energy to the water molecule. The water molecule, this energy is going to be absorbed. The molecule which may not be in a stable position, so that with respect to their position, the molecule is going to be vibrating, and the energy which is going to be transferring from the one molecule to the other molecule. So here the position is not going to be changing here. The vibrations which are perpendicular, that means here the transverse waves are going to be generated on the surface of the water, and which are moving all the 360 degrees. Okay. So that is the disturbance, you can say that. So here waves are going to be generated, and which are to be traveling through the same media, and which does not itself move as a whole. So like that here the same example just now we have been discussed. This is the example. Okay. So this is the example. Water falling on a dam, a glass window getting broken, and a stone thrown from a distance, and the turbine moves with the water falling on a glass. So these are the example for that. The thing is that here this is about the light energy, such a energy, how it is going to be moves here, propagating. So that the propagation of sound energy, okay. So from one place to the another place, like a wave motion, okay. So here the each particle of the medium which is going to be vibrating with respect to their mean position, and which may transfer the energy to its neighboring particle. So that here these theories, that means one is the corpuscular theory which was proposed by the Isaac Newton in 1675. Okay. And other theory which is wave theory that was proposed by the Huygens in 1678. Okay. There are two contradiction between these two theories here. Everything, the energy which is going to be propagating by the particles only, not by the waves, which was said by the Isaac Newton, according to his corpuscular theory. But some of the properties of the physics which are here fail to explain clearly. Okay. So at that time, Huygens he was entered into the picture here, and he said that not by the particles, okay, the energy which may be propagating and transferring from one to another place, that was not by the particle, but which can be by the waves here. Wave may include the particles, isn't it? So that was said by the here Huygens theory. So whatever the failures which was taken out by the corpuscular theory successfully explained the Huygens according to his wave theory. Okay. That is the case we are going to be considering this Huygens wave theory. So according to the wave theory, the light source which may sends out the waves in all directions. Okay. since a medium which is going to be requiring a propagation of wave, hypothetical medium, that was ether. Einstein said that. Okay. According to the special theory of relativity, the entire universe which is filled up with the ether medium. Okay. So here, which was assumed to existing in providing in all spaces. Next is that there are relative merits of the each of these two theories, which is by the Newton's corpuscular theory and as well as the Huygens wave theory. So here, corpuscular theory could explain the rectilinear propagation of the light and phenomena of reflection, refraction, and dispersion, and theory fails to explain the phenomena of interference, diffraction, and polarization. Okay, so this was successfully explained the concepts of the reflection, refraction, dispersion, all these rectilinear propagation of light. But it is failed to explain the properties, another properties, most important properties, which are interference, diffraction, and polarization. Okay, according to corpuscular theory. But whenever the wave theory, which is comes and enter into the picture, Huygens could explain the phenomena of reflection, refraction, and dispersion. And a satisfactory explanation or a rectilinear propagation on the basis of wave theory, which was given by the Thomas Young and Fresnel. So also demonstrated the phenomena of interference. So here the acceptance of the Huygens wave theory and Fresnel's, which was demonstrated the phenomena of the interference. So okay, so here the thing is that by accepting the wave theory becomes a very that means when now Foucault and Michelson, they have been Michelson-Morley interferometer. Okay, so they have been showed that experimentally that the speed of light which is lesser than the in water than the air speed of light. So what is the value of the speed of light, Andy? 3 into 10 power 8 meter per second or 3 into 10 power 10 centimeter per second. That is the speed of light. Okay. So here, the speed of light which is less in water than the air. And is the reverse as per the corpuscular theory. According to the wave theory. However, the discovery of the photoelectric effect. So what do you mean by photoelectric effect? Who proposed this means? Einstein. Whenever such a light of an incident, intensity of light which is going to be falling on any alkali metals, so that these metals are emitting the electrons. These electrons are photoelectrons. Due to the photoelectrons, the electricity or the current is to be produced. That is photoelectric effect, which was proposed by the Einstein. So here the photoelectric effect is to conclude the emission of the light is a corpuscular in nature. Okay. So why? Because of there is only one particle. The particle is an electron, which is having a mass and which is having such a velocity, so that which are to be moving from the cathode to anode, and it is to be constituted the current. So that is the thing here. But the quantum theory of light, the postulates of the emission of the light and the energy in terms of quanta, Max Planck, he proposed that. Okay. So which is called the photons here. The energy of the photon is equals to h nu, where h is the Planck's constant, nu is the frequency of the radiation. And what is the h value? Most important, 6.623 into 10 power minus 34 joules second. Is it clear? So that is the h value. And this theory could satisfactorily explain the phenomena of photoelectric effect. Wave theory, whereas the wave theory has failed to the account for the experimentally observed effects. And here the nature of the particle, that is the light and other phenomena, which can be explained only on the basis of the wave theory. So the dual nature of the light, uh, presently accepting the and out, and sometimes we have to think about in terms of the photon, and sometimes we have to think about it, which is a wave. Okay, so Huygens wave theory, which gives the explanation of the phenomena of reflection, refraction on the basis of the wave. And another important characteristics of the wave motion is the phenomena of interference. So, which occur when two or more waves, which are to be coinciding in a space and time, and those are going to be superimposed. Uh, that means the superposition of two simple harmonic motions. The interference occur for the example in region which is to be reflected, and the incident, here waves coincide here. So another important example for the interfering means here the wave motion, which is confined to a limited region of the space, such as a string which is a two ends fixed, or a liquid in a channel. And this was demonstrated by Thomas Young in 1801. So this was the strong experimental evidence about Huygens wave. So in wave motion, two types of waves. One is the longitudinal, another one is the transverse wave. What do you mean by longitudinal? Longitudinal means the longitudinal wave is nothing but here. The propagation of the waves, and as well as the vibration of the particle, both are to parallel to each other, then the type of wave you can call it as a longitudinal wave. Compression as well as the rarefaction, which may be observed in the case of longitude. So what do you mean by transverse wave? The vibration of the particles in one direction perpendicularly, if the wave is going to be propagating, then that type of wave is nothing but a transverse wave. What do you observe in the case of transverse wave? Crest and trough. Crest and trough. Okay. So that is to be observed. So here, in a transverse way, the motion of the particle of the media vibrate with their mean position, and in a direction perpendicular to the direction of the propagation. So parallel to the direction of the propagation, both are parallel means longitude, and one with another, which is perpendicular means transverse wave. So here, by developing the wave theory, Huygens wave theory, he has been assumed that the light waves has a longitude, isn't it? So Huygens could satisfactorily explain about the phenomena of the reflection, refraction, and double refraction. Okay, where they observed in crystals. So what are those quartz crystal, calcite? Okay, so CaCl, cesium chloride. So many crystals are there. Okay, so that means here, along the principal direction, that means the ray which is to be entering into the crystal means, along the principal axis, if it is going to be traveling and emerging out, that is an extraordinary ray. But some deviation is going to be takes place, and emerging out, that is ordinary ray. But the thing is that you need to be noticed that here, emerging ray as well as the extraordinary ray as well as the ordinary ray, both are parallel to each other. In the case of when these two rays are traveling through a crystal, either in a quartz or calcite, whatever it may be here. But emerging rays both are parallel to each other. But the thing is that here, the speed of velocity of these two rays are different. That you may be discussed in the coming classes. But the thing is that here, that is the double refraction. Okay. So that was successfully explained by this. And Fresnel and Young, they have been suggested that light waves are a transverse waves, and they could explain the satisfactorily the rectilinear propagation of light and the phenomena of interference, which may be characteristics of any wave phenomenon. So irrespective of whether the waves are longitudinal or transverse. So here we should know about the what is Huygens principle. So according to the wave theory, a point source of light. So this question is asked so many times. Okay. So please go through this Huygens principle. According to the Huygens wave theory, a point source of light, when it is placed in an isotropic medium, okay, isotropic medium, which may emit the light waves in all directions. And these waves, which may travel in the form of expanding concentric spheres with a uniform velocity 3 into 10 power 8. So you can see here, this is the spherical wavefront. This is the cylindrical wavefront. Okay. So with the point source as a center, if the disturbance is to be takes place, it is going to be reach all the particles and which are lying on the surface of the sphere. So such a sphere is called as a wavefront. What do you say? Wavefront. So thus a wavefront may be defined as uh, the locus of points having the same phase. Locus, not focus. Locus of the same points which are having the same phase. So the shape of the wavefront depends upon the shape of the light source and its distance from the source. So what do you mean by spherical wavefront? So the spherical wavefront is a portion of the spherical surface and all the particles are the same phase. And what do you mean by cylindrical wavefront? So cylindrical wavefront means when the source of light is linear. Then in an isotropic medium, the wavefront takes a cylindrical shape. So each particle on this cylindrical surface will be the same space. Next one is the plane wavefront. So a plane wavefront is a plane surface through which a wave disturbance passes. And all the vibrating particles are in the same phase. So here, the vibrating particles which are in the same phase, a portion of the spherical wavefront or a cylindrical wavefront, which is at infinite distance from the source. In previously, which are known distance, okay, whether it is a spherical or cylindrical. Getting my point? So here Huygens principle, which may be providing the geometrical method of finding the shape and position of the wave. Shape and position of the wave. at any instant of time. So if we know the shape and position at any other previous instance, according to the principle of all the points on the wavefront can be considered as point sources for the prediction of the spherical secondary wavelets. Later on, at any instance, the position of the wavefront will be the surface of tangency of the secondary wavelets. So here the condition is that let a wavefront originating from the source S is here. That is not shown in the figure. And if it is going to be reaches the position PQ at time equals to 0, maybe, yeah, S is a source here. PQ, if it is going to be reaching like this, the wavefront, and which may be like a secondary source from which spherical waves which are to be spreading out. After small t time, there will be a series of wavelets which centers at 2, 3, 4, etc. of radius. And see the constant of the radius. Okay. Velocity of the disturbance, wave disturbance, and the wavefront, which may be given as after dividing all these things, which is RS. Okay. So from the examination point of view, so here the thing is that in previous section, the figures which are to be indicating 1.1a as well as the 1.1b, these two are the, one is the spherical wavefront, another one is the cylindrical wavefront. Okay. So these two are to be by the examination of these two cylindrical as the spherical waves, it is to be evident that the spherical wavefront is propagated as a spherical, and plane wavefronts are propagated as a plane with a speed 3 into 10 power 8 meter per second. And it is also noticed that Huygens method, which may involve the three-dimensional construction. Okay. So Huygens principle, which may assumes that the wavelets, which is effectively only at the small position, and which is a tangential to the envelope of the surface. So let a ray may be defined as the line joining the center of the wavelets to the small portion, and which is also may expect a wave radiated backwards, say R dash S dash. Forward is RS, backward is R dash S dash, apart from the once radiated forward in this figure. This may be resulted that here the intensity of a spherical wave is not a uniform in all directions, but it is going to be varies continuously from a maximum uh, in the forward direction with a minimum of 0 in the backward direction. And the thing is that here, according to the Weisheit and Kirchhoff's contribution of the wavelets in a given direction, if it is going to be making an angle theta with the direction, and which is also proportional to the 1 plus cos theta by 2. Thus, in the forward direction means if theta equals to 0, okay, that is the intensity should be maximum, and if it is in the backward means theta is 180 degrees. Theta 180 means cos 90 0. Okay. There only the intensity becomes 0. So Huygens principle can be applied to the all waveform. So let us discuss about this phenomena for the reflection as well as the refraction. So we can go for this. So here, let us consider a plane reflecting surface. Which one? This one. M and M dash. M and M dash. Which is a plane reflecting surface. Reflecting. Underline this. So let AB is a plane wavefront. This one. This is a plane wave. And which is striking the surface MM at position A. This one. At time t equals to 0. What will happen here? This is the smooth surface. Okay. So this is a normal. The thing is that um, so if it is a smooth surface, immediately if it is going to be reflecting back. Okay. If it makes an angle theta or incident angle, if we say that with respect to the this is a reflect. So the thing is that let c be the velocity of light at time t, and for the edge b of the wavefront, this is a and this is b, and to reach the point c, that is in the absence of the reflecting surface mm dash, the incident wavefront AB, this is AB na incident wavefront, incidenting na on the smooth surface, immediately reflection is going to be takes place. Why? Because of it is smooth. And in the absence of the reflecting surface, the incident wavefront AB would have reached the position CD. Okay. The position C, and which is the maybe here. So, but in the presence of mm dash, the wavefront advances the particles between A and C, which may behave like a secondary wavelets, So that if you are going to be applying the principle of the, what do you say, Huygens theory, wave theory, so we can easily identify that here the wavefront which is going to be touching the surface mm dash, and which become on the source of the secondary wavelets, and which is to be spreading in all the surroundings of the medium, and there should be the disturbance from the point B, which is going to be reaching the point C at a time small t, and the secondary wavelets from the point A, which would be attained in a radius BC equals to small r. Let you consider small ct. Okay, BC equals to. So see the speed into time. That means how much of the distance which may be traveled by these wavelet. Getting my point? So the position is you can easily find by taking the consideration of the point A as the center, and which is to be drawing with the radius of the sphere, that is CT. So the CT be the tangent at D to the wavelet from the point A, and then uh, the thing is that here then the CD, which is to be representing the reflected wavefront after time t. So by considering small p on AB here, on AB, if we are considering P, let PQR, PQR, which one? This is the point P and PQR, PQR, okay, which is parallel to the BC. So let QR and Q dash QR dash, which are representing the perpendicular draws from the Q to the C. All these calculations by doing this uh, with the right angles here, by simplifying this, you can have the that same distance here. That is AD dash equals to CT equals to AD, that is equals to BC. So QR dash equals to QR, which is indicating that here the wavelet from Q touches the wavefront CD dash at R dash, and this is true for all the wavelets emanating from any point between A and C, and CD dash, which is represent the reflected wavefront. Okay, so here by considering all the conditions here, BC equals to AD dash, by doing all these conditions and calculations, the angle of incidence, which is equals to the angle of reflection. So that is indicating the law of reflection for the Huygens principle. So the same thing, but the thing is that here refraction. So refraction means here we have been already discussed that. Refraction means you may observe the light ray which is incidenting and entering into the other media, one media to the another media, and bends at the normal, bends at the normal. Then this phenomena which is related to the refraction. So here M1 and M2. So MM dash is the smooth surface. But the thing is that here different media is to be considered. Getting my point? So same MM dash is the refracting surface, which is to be separating the two transparent medias. One is the rarer and another one is the denser, air and glass. Okay. And here C1 and C2, which are to be representing speed of light in air and speed of light in glass. Okay. So from the diagram only, what is the incident plane wavefront? APB is a plane wavefront, and which is to be meeting at the surface MM dash at A, and which becomes the source of the secondary wavelet set t equals to 0, and t with the time taken for the edge of the wavefront to reach the point C. So BC equals to speed of light, speed into time is nothing but a distance here, C1 to T. And if it is the glass medium is absent there, the wavefront APB would have an advance to the position of CRD. The presence of the refracting surface as the wavefront advances the particles on the AC become source and secondary waves, one after the another. So here also same principles are to be applying here. The thing is that here you need to calculate and you have to be equating, and here which is going to be coinciding and doing the all the calculations which can tell about the here Uh, Here sin A by sin R equals to, what do you mean by sin A and by sin R? Which is a Snell's law. Okay. Refractive index formula. Mu equals to sin A by sin R. So, sine of the incident, the ratio of the sine of the incident angle to the sine of the refracted angle is nothing but a refractive index, which is nothing but a Snell's law. So, that is the case. Next, to total internal reflection. Where do you observe fiber optics? Okay. On the principle of the total internal reflection only, the signals which are to be carrying from one country to the another country. Okay. Easily communication system, entire communication system, which works under the principle of total internal reflection. Okay. When the laser light or the beam which is traveling through in any optical cable, fiber optics. So there only we are using this phenomenon. Okay. The phenomena of total internal reflection, which can be observed only when the light passes from denser media to rarer. Okay. Denser to rarer. So by considering the light which is situated at the point O with a denser medium, and mu1, mu2 be the refractive indices of the denser as well as the rarer medium. When the light ray is normally incident to the surface, it travels the same direction. Okay. But if the incident ray makes an angle θ1 with the then the refracted ray which moves away from the normal making an angle theta. That is the case. So according to the law of refraction. So sin θ2 by sin θ1 is mu2 by mu. So if mu2 is greater than mu1, the angle of refraction θ2 will be greater than the angle of the incidence. So applying the conditions, you can easily find out that here the theta c, that is no refracted ray, that is a critical angle. Theta c is the critical angle, which is 41.80 degrees. Okay. So this you can imagine that this is a fiber optics or optical cable here. So this is the beam, laser beam, which is passing. So which may have how the signal is going to be passing. This is the 1, this is the 2, 4 and cladding. In detail, we will discuss in the 4th unit. No need to worry. Okay. Fiber transmitting a small fraction of units. This one. So in other direction is also you can see here the appearance of the outside world for a fish in water can be found in the making the age of phenomena of total internal reflection. So in this figure, a swimmer inside the water will appear to float on the upper surface here, and uh, of the water, and a tree at the shore looks as if it is floating in the sky. Okay, to the fish. So similarly, the rising and setting sun appear to be little above in the sky. The appearance migrates in deserts in only due to the phenomena of continental convection. So due to the high temperature, the air near the surface of the earth gets heated up and hence forms a rarer. So as a result, the rays from the trees get totally internally reflected and resulting that in the formation of inverted image if seen by a distance observer and the observer experience the illusion of water in deserts the presence of the image. Next, the phenomena of interference. So here the light traveling along the x direction, which is represented by a sine 2 pi x by lambda minus small t by capital T. Y is the displacement, A is the amplitude. Okay. And actually, another one is the propagation constant. Lambda is the wavelength. Small t is at any time, small t. And capital T is the time period. That means which may be indicated here frequency. Okay. So or else you can write it down that this equation becomes a sine 2 pi x by lambda minus Vt. Nu t, not Vt. Nu means frequency. Okay. Number of vibrations per second. The reciprocal of the time period which may gives the frequency. What is capital T and E? 2 pi by omega. Okay. Or else this equation may be written as y equals to uh, sine kx minus omega t, where k is the propagation constant, omega is the angular frequency. And here you can easily notice that A is amplitude, lambda is wavelength of the light, and capital T the wave period, x is the wave position, nu is the frequency, and omega is the angular frequency, and k is the wave vector, 2 pi by lambda, that value. So, as the intensity of light at any point which is proportional to the square of the amplitude. Okay? X square is A square equals to I. So then the term 2 pi x by lambda minus small t by capital, which represents the phase angle. Okay. So here the thing is that this is also asked as an essay question. But by considering two waves of equal frequency, okay, angular frequency and amplitude traveling with the same speed along the x direction, let the phase difference between two waves, which is phi, this one. Then the two waves which are represented y1 equals to ym sine kx minus omega t minus phi. Y2 equals to ym sine kx minus omega t. What is the phase difference between these two waves? Phi. Ym is the maximum amplitude. Okay. So according to the principle of superposition, what do you mean by principle of superposition? And x equals to x1 plus x2, y equals to y1 plus y2. Okay. The total displacement of two or more waves is equals to the displacement of the sum of the individual waves. That is nothing but a superposition principle. అధ్యారోపణ సూత్రం అంటాం తెలుగులో. సో హియర్ ఇదిగో ఇక్కడ ఇచ్చినట్టు y ఈక్వల్స్ టు y1 ఈక్వల్స్ టు y2, ఇది y ప్లస్ అండి, ఇది y1 ఈక్వల్ టు y2 కాదు ఇక్కడ ప్లస్, హియర్ y equals to y1 plus y2. Print mistake. Some textbook they may be written as x equals to x1 plus x2. This or this. Both are same. Okay. So by adding these two, sine kx minus omega t minus phi plus sine kx minus omega t. So sine a plus sine b, 2 sine a plus b by t into cos a minus b by t. Substitute చేద్దాం. చేసిన వెంటనే y equals to 2ym cos phi by 2 sine kx minus omega t into phi by 2. So you got it, this equation, and apply the conditions. And here we noticed that in figure 1.11, a stable interference pattern can be observed if we have two sources of light waves having the same frequency and nearly the same amplitude and possessing constant phase difference between them. Such sources are called coherent sources. So you can easily observe that so interference effects can be observed on a screen. See here. So in the case of interference, you may be observed that the bright, dark, bright, dark, bright, dark fringes. Okay. So in this, what do you mean by temporal coherence? If two waves maintain a definite relationship between their phases at a given instant of time and a certain time later, these are to be said that temporal waves. So this is the source S1. So by considering a point source, a quasi-monochromatic light. So which may emit the light in all directions. Consider the light traveling along the path SP1, P2, SP1, P2. If the light is traveling in this direction, the phase relations. So here the points P1 and P2 depends on the distance. These two, this distance at the coherence length of the light, which may be capital L of the light is different and the so speed of light into distance c tau. Okay, where tau c is always. So if L equals c tau tc, tau c is called coherence times c is the speed of light. So here temporal coherence, which is characterized by the two parameters. One is the coherent length, capital L, and coherence time, tau c. So if the light which is to be emitted in the form of short wave trains and as the phase of the one wave train would be remains constant with respect to the another uh, for about 10 power minus 10 seconds, which is going to be implies the two waves are temporarily coherent but a period of time about 10 power minus 10 seconds. This is called the coherence time, and the average time taken for these two is nothing but a coherence time length. That is tau c. Whereas coherent length, which is the light wave of the wave packet over which it may be assumed to be sinusoidal and which is a periodic phase. You can see here up to this LC, which is a coherent length. Here starting and here ending. Vibration. Okay, along the x direction. the wave is going to be moving, propagating. So by tomorrow we will discuss this spatial coherence, Young's experiment. Is it clear? So we will discuss this concept by tomorrow. Okay. Right. All the best.